Hello, good afternoon, good morning. My name is Chiara Benetti, and on behalf of ETA Florence Renewable Energies, technical organizer of today's event, I welcome you to IEA Bioenergy Webinar on the integration of biogas system into the energy system. The webinar will be presented and moderated by Professor Jerry D. Murphy, Director of the SFI Marai Center for Energy, Climate and Marine, Director of Bioenergy and Biofuels at the Research Environmental Institute of the University College Cork, Ireland, and by Jan Liebetrau, Head of Department Consulting and Research from RITEC, Germany. After these two presentations, there will be a Q&A session, and you can participate in this Q&A session by typing your questions in the Q&A tab that you can find at the bottom of your screen. You can type your questions during the whole webinar from the beginning until the Q&A session, and the speakers will have the possibility to reply to your questions by typing the answers directly in the Q&A tab or by answering live during the Q&A session. Please do use the Q&A tab only for questions and do not use the chat box. The webinar will be recorded, and the recording and the presentations will be available from tomorrow on IEA Bioenergy website. From my side, that's all. I hope my instructions were clean for all of you. And now I give the floor to Professor Jerry D. Murphy for his presentation and introduction. Thank you, and enjoy the webinar.
Thank you, Chiara. We appreciate that. So we welcome you all here on behalf of IEA Bioenergy. We are Task 37, and we examine biogas, anaerobic digestion, circular economy systems. We have a website with lots of data, lots of reports, and this website will synthesize a report we wrote over the summer. I think it was published in August 2020. It was led by Jan and included for David Wall and myself and others. The report is Integration of Biogas Systems into the Energy System. Jan is Head of Department Consulting and Research at RITEC GmbH. After obtaining a diploma in civil engineering, he received his PhD at the Bauhaus University Weimar on the topic of control systems for anaerobic treatment of organic wastes. From 2006 to 2007, he was a visiting scientist at the Alberta Research Council in Canada, working on integrated manure utilization system. From 2018 to 2019, he worked for DBFZ in Leipzig, the German Biomass Research Center, and since 2020, he leads RITEC GmbH. His expertise is process control of AD systems, emissions from biogas plants, and as of next year, Jan will take over the leadership of Task 37. Over to you, Jan.
Thank you very much, Jerry, for this introduction. And as already said, the idea today here is to present the report, which was just mentioned. And first of all, I would like to thank all the authors of the report. Of course, it was not only me, I was leading the task, this is right, but Peter Connors from DBFZ, and Ospire from Switzerland, and Jerry and David from Ireland as well contributed to this report. It is about integration of biogas systems into the energy system. And my task here today is to introduce you the flexibility of biogas systems. So this is mainly flexibility of electricity producing biogas plants. So you have a CHP on site. And Jerry then will give the second presentation on power to gas systems. I would like to talk today here about technical aspects of flexible plant operation, economics, exemplars of flexible operation. And of course, at the end, there will be some concluding remarks. Why would you actually try to flexibilize a biogas plant? In the past, they have been built to have a stable, constant, stationary operation. However, the energy system is changing a lot due to wind and solar, more and more wind and solar into the energy system. We have a fluctuation of energy production. On the other side, we also have a fluctuation in demand. And to meet this input and out on this demand, to match this, we need actually flexible energy supply. And biogas can do that other than wind and solar. And I think this is a task for the future, that every energy producing unit has to adapt to the demand and the production in the grid. A second option is the direct supply of a fluctuating demand of industrial facilities or other energy customers. In particular, also in areas with an unstable grid situation, biogas could function as a standalone solution. And then also you have to adapt to the needs of your customers or your industrial facilities. Just for the biogas plant itself, it's always good to have a shutdown scenario or even a reduction of your load. And this is, in case of maintenance, for instance, is good if you can safely steer the capacity and the load of your plant. And last but not least, I already said a little bit about this. We have power to gas as an option. Then biogas can function as a link between electricity and gas grid, but Jerry will look at this later. When we go for electricity, we have different demand levels, different demand curves. If you look at the grid, of course, as already mentioned, we have wind, solar into the grid. And then you have a complete, depending on how much you have this in your grid section, you might have a complete different load on the grid. And grid operators have to respond to that. And biogas can help support for grid stabilization in such cases. On the other side, of course, there's the electricity market. And this market follows these fluctuations, and the price will follow these fluctuations as well. So it's also for electricity producers interesting to produce electricity in times where it costs or the price you can obtain is high. The other thing is, if you have direct supply of a farm, for instance, as you can see on the right side, then of course you have, depending on the machinery you're using, you have a demand change. And if you want to follow this and you want to reduce the externally bought electricity, then you would need to produce in electricity in high times and lower the electricity production in times where the demand is low. A complete different story is the heat. If you have a CHP, you have heat, which you only use to, let's say, roughly 10% for the process itself. And the other heat you could actually use to sell it, to use it on site. The heat demand follows a completely different pattern than the electricity demand. And usually biogas plants are linked to housing, heating, stable heating. So this is a very seasonal curve you can see here. And this is, of course, if you have a heat customer, a challenge to combine your electricity production, your flexible electricity production, and this heat demand. And this is one of the tasks, if you go for flexible operation, that you combine it. On the other side, the seasonal heating scenario offers you also the option to optimize your revenues. If you produce more electricity in the wintertime, for instance, then you produce, of course, also more heat, and then you can sell more heat. And this might also be a way to optimize your revenues. Last but not least, if you have a standalone fuel station, You might also have a certain fluctuation. As you can see here, if you fuel logistics fleet, then it might be quite constant depending on the fleet. But if you fuel, for instance, farm or farm operation, larger farms, then of course there is a highly seasonal fluctuation, and you need to cover that with your gas production. Summing up all these demands, in order to meet this, you need to install a certain overcapacity at your plant. Any flexibility means overcapacity in order to have times of lower production and times with higher production. And that also means idle capacity for periods of time, which means additional costs. So you have a higher technical effort because you have to organize these fluctuations, and you have idle capacity, and you need to be aware that your benefit from the flexibilization need to balance out these additional costs. Standard operation or standard procedure for flexibilization of a biogas plant is usually the increase of the CHP capacity. Take care that you also make sure that your grid operator agrees to this and allows the grid access in the same order of magnitude. Increase of gas storage capacity in order to balance the changing gas utilization rates. You might also look into control of biogas production rate. I'll talk about this a little bit later. Another option, additional options to improve your flexibility are power to heat. Of course, the most flexible way is producing biomethane, feeding it into the grid, because then you completely separate gas production and gas utilization. And last but not least, power to gas, which will be a topic later on. Flexibility, the quality of flexibility depends a little bit on how you operate that. If you have, as the upper graph shows, a very simple standard on-off scenario, which you run every day the same, this is from the requirements to the plant and to the plant operation, a quite simple processing. The other option is, or the other way of flexibility is that you really react on the change on the market or in the grid situation, depending what your aim is, what your target is. And then, of course, you need, for first of all, a prognosis, somebody who will tell you how your energy provision should look like in the next hours, the next days. And second, you need quick, fast, in best case, even a remote control of your plant in order to respond to these prognoses. And here are different operation modes, different scenarios compared for such scenarios. The first one, the weekly schedule, is very simple. So you set on Sunday how you will operate next week, and then you can actually fulfill the requirements of markets, which are named here, day-ahead market, for instance, ancillary services. And your technical effort and your control effort is, in such a case, quite low. But of course, this also means that you cannot really produce the electricity to the best times, and therefore the revenue will be lower than in the very right option here. This would be real-time control. Then you could even optimize your energy production during the day. You are able to take part in all markets of simply day-ahead market. You can even go into intraday market, and you have the full range of ancillary services. Then, of course, you need remote control. Technical effort has to follow this, and your chance to gain money from that to increase the revenue are highest with such a system. Technical aspects, of course, include the capability of your CHP to run flexible. And in the past, as I already said, producers looked at a constant operation. Now they have to actually facilitate part load operation or standby start-stop operation. And as you can see here, there are some requirements to the CHPs, but I can say that the producers very quickly adapted to this new situation, and they improved the starters, for instance, or they adjusted the startup procedure in order to be very fast online with the machine, so that this has changed a lot. And if you buy a new unit today, you can be sure actually that, or most packagers will offer you such flexible operation packages. When you look at CHP operation, and some people might think, oh, I go for part load operation because then I don't have the start-stop issue. Then you need to be aware that the efficiency actually goes down quite dramatically. And if you look at the sometimes very slim revenues, additional revenues you get from a flexible operation, you need to look at if this is not even eaten up by your loss of efficiency. Second point I would like to highlight here is that the larger the engine, the higher the efficiency is usually. So if you opt for, or if you look into flexibilization, if you think about having 2 engines, for instance, instead of 1 large engine, then you need to be aware that these 2 engines will have a lower efficiency than the 1 engine. So flexibility might mean also that you increase your capacity, have a larger engine with a higher efficiency, and this might add to your revenues. Part load operation not only reduces efficiency, it also increases methane slippage. And so it's also from the environmental point of view, part load is not a very good idea. When we go step away now in the production line, or step down in the production line to the gas storage, last line is the CHP, we had this, now we go to the gas storage. Then the gas storage has actually the task to balance out deviation between gas production rate and gas utilization rate. In the standard stationary operation, this is not very difficult. The gas storage doesn't have to be quite large. And everybody needs to be aware that the gas storage capacity is limited. However, in a flexible operation, the story is completely different, because gas utilization rate might all of a sudden exceed the gas production rate by factor 2 or even 3. It depends on how much overcapacity you have, or it might mean that you have actually no gas utilization at all, and all produced gas needs to be stored. And the gas management is not, at many plants which have been constructed for stationary operation, the gas management is not made for flexible operation, and it might need some upgrade in order to fulfill the demand. A very simple upgrade is, of course, increase the gas storage. You might even think about additional clean gas storage. Very often the sensor systems for the measurement of the filling level are not very precise. So this has to be upgraded in order to have the knowledge about precise available gas amounts. Installation of gas management transportation system between gas domes. If you have double membrane air inflated gas storages, then the gas transportation between these domes, if you have several of them, is not always 100% safe. So maybe an active gas transportation system might support there. Upgrade of the gas transportation lines in order to cover or be able to run with the higher throughput, and upgrade of gas treatment devices, gas drying, for instance, or desulfurization. These units also need to be able to cope with the higher throughput. If your gas management or the gas storage is still not large enough and you don't want to increase the gas storage capacity, another option is a feeding management in order to alter your gas production rate. Then you have the option to adjust the gas production rate to the gas amount which is needed. But this requires usually a model-based control, because this gives you information on the gas production, what you can expect of different substrate mixes. This is an example for such a model-based control algorithm. And what you would like to set there in order to steer your gas production rate is the substrate type. If you have different substrate, they respond differently, they have different gas potential. So you might select which substrate you use. And second point is the amount of feeding. Very simple, tons per day. You can look into that also to steer your gas production. And your control variable would be, of course, the gas storage filling level in order to have a safe operation of your biogas plant. This is an example of an operation as it has been done at the DBFZ in Leipzig in Germany. The gray vertical lines here show the on times of the CHP unit. So this was the schedule for these 9 days here. And what the model would do is then predict for 7 days ahead. And according to this schedule of the CHP, the model tries to actually stay within the boundaries of the gas storage filling level. Then the first day operation happens, and the blue line in the bottom, you can see that the filling level of the gas storage is within the boundaries, which are also shown here. And so this is going on day for day. You always have a prediction of 7 days ahead. And then the model also is comparing the actual gas production with what it has predicted in order to adjust a little bit. And you can see that the model was able to run within this boundary. Without the model, you see the dotted line here, then you would exceed actually the gas storage capacity. So you would not be able to run such a scenario with your CHP operation without this adjusted gas production rate. If needed, or I think for full control of the overall plant, you would need also some additional variables to include in such a model. These are, for instance, substrate prices, also prices which you can obtain from the APEX, so the electricity prices, heat prices, in order to be able to really estimate if your schedule is economically viable. So if you can actually gain profit from this, then the model, of course, needs to be much more complex and much more sophisticated. One major or one point I would like to take out here, and this is essentially the storage capacity. If the sun radiation on such a double membrane gas storage is quite high, then temperature can increase up to 70 degrees. We have tested this at this gas storage, which you can see here. And this changes, of course, the temperature of the gas inside. And if you have a change of 30 Kelvin in a day, then this can change your storable volume by 20%. This is not only due to the expansion of the gas due to the increased temperature, it's also the water uptake, which is much higher as increased temperatures. And you have to take this into account, of course, if you run your gas storage. Otherwise, you will have overpressure event and you will lose gas into the atmosphere. Now I would like to discuss a little bit on the economics of flexible operation. As already said, overcapacity is needed, and this means usually you have additional CHP. And you can see that estimated costs for artificial biogas plant, which we have chosen here, would be 64% dominated by the CHP. So the CHP actually is the most expensive part. You have also other investments as given here, for instance, the gas storage capacity, but CHP is the most expensive part. And here are 4 options calculated by my colleague Peter Kornetz. And I would like to highlight only here that if you double the CHP capacity by a 500 kilowatt unit, reference plant is on the very left side, and doubling the capacity would be the second flexibilization option here. This would reduce your operational hours from 8,000 down to 4,000. And this would increase your power production costs. This is the second line on the bottom, by 3 cents. Here's 2.5 cents given here. So almost 3 cents, your electricity production costs will be higher if you double the CHP capacity at a 500 kilowatt plant. And this cost, of course, you have to somehow balance out. You have the option to follow the market price over the day. In Germany, this looks like this here. We call that a double hump over the day. And if you put your gas production right into this high pricing times, you might be able to increase your revenue a little bit. And this then, of course, looks like that. And at the moment, the price difference over day is something between 0.5 and 1.5 cents per kilowatt hour, what you can actually achieve there. And this is at the moment not covering these additional production costs, as I already mentioned. But of course, this will change. In Germany, we have a phase out of coal-based electricity production. And once these coal-fired CHPs are out of the grid, then I think the fluctuations will increase a lot. And then, of course, price change will increase also. This is a prediction made in 2016. And there is the price difference predicted here. But this is for a 12-hour operation. So this is, of course, if you have a, let's say, 6 hours of operation instead of 12 hours operation, then you can, of course, go even more into the maximum price. But if you have a 12-hour operation, you're forced also to take times where prices are not so perfect. And this is also not considering the winter and summer situation. If you switch from summer to winter, then you might be able to sell more heat. This might increase your revenue as well. The second point might be that in winter electricity, prices might also be a little bit higher than in summertime. Another market, besides from the physical electricity price, is the ancillary services. This is when you offer products to the grid in order to stabilize it. They have certain requirements in time and duration, and these are options here where you can actually participate in this market. But this is something which is specific to the grid operator, and there you have to look into the details of your grid operation. Now I would like to discuss some exemplars. And in Germany, we have an extra support for flexibilization of biogas plants. And according to this, we have a lot of plants already in a flexible mode. They have upgraded. And however, this is more or less a technical standby. So they are not forced to operate flexible because at the moment, as already said, the revenues of such an operation are very limited. But these are 2 examples here of such plants. They have an overcapacity, in this case here, of almost 5 times. So this has been, as said, covered by this additional tariff. They have a heat storage of 1,000 cubic meters of hot water in order to cover the heat which is produced, to store the heat which is produced during the on times of the CHP. And the revenue which is at the moment gained from this operation is something like 1.5 cents per kilowatt hour. Second plant is very similar. They have a little bit smaller hot water tank for the heat storage here. But they also increased their gas storage capacity, and they have a flexible operation since 2019. I think these plants, they show what biogas is capable of, and I'm really curious to see how this operation will look like in 5 or 6 years once the electricity market will change. This is my idea about flexible operation. Another option is, something which is required on such a flexible operation is that the different plants have the opportunity to bundle their services. Because if you go with one biogas plant into the electricity market, it's difficult to actually organize your trading system, to organize that you get the high times of electricity and you steer your plant properly, things like that. This is not something a farmer could actually do very well. That's why we have traders and companies who offer such services to the farmers, to the biogas plant operators, and they bundle a lot of renewable energy facilities and then trade the electricity and also offer services to the grid. And this is here an example of such a trader in Switzerland, which has been able to bundle around 30 megawatt of production into their portfolio. And we also have in Germany such companies, and they even optimize their product and offer you an increase of the income with an optimized schedule of your biogas plant. And I would like to conclude. To our opinion, the perception of the role of biogas has changed. In the past, it was more or less production of energy based on waste, so the waste treatment was the focus. Today, we see it as a source of renewable energy, and this production function has to actually cope with the requirements of the new energy system. And biogas is actually quite good in offering services which are in need, which the new energy system is in need of. And this is simply due to the fact that we have the photovoltaic and wind energy fed into the grid, which requires other energy reactors which can produce if PV and wind is out. Biogas plant operation can be controlled extensively. I think I showed that, and this comes with a very high level of flexibilization. And that's why we think that biogas system actually can be an important tool for actually steering and also supporting electrical grids in the future, and also supply heat when it is needed. Jerry will discuss in the following presentation a little bit more on the natural gas substitution by means of biogas. Flexibility of biogas can facilitate energy delivery to the electricity grid. As already said, we can actually cope with different electricity demand profiles, heat consumer, as I said. We can support decarbonization of gaseous fuels. And biomethane, we can directly deliver to local consumers if they are needed for transport, haulage, and buses. This would be the standalone biomethane production. And that's why biogas can play an essential role in virtual power plants. And this is what I show to you in these two exemplars of these virtual power plants. So that's from my side. And I would hand over to Jerry now and hope I kept my 30 minutes.
Thank you, Jan. I might ask you to answer some of the questions. I've answered a few. If you look at the Q&A, so you might try and type some answers. I'm going to do my best here to share screen. I am not the most Microsoft PowerPoint. I really hope this works now. This would be nice if it works. Play from start. Jan, do you see my screen?
Switch display, please.
Switch display.
Okay.
Fabulous. Okay, thank you very much, Jan. So my piece in this is to look at when there is too much electricity on the system and how biogas can actually take electricity off the system. So it's a very different perspective than producing electricity or energy on demand. This work is co-authored with David Wall and a lot of my colleagues in MRI and in IEA Bioenergy. Again, this report is available for free online, and there's lots of other pieces of work and case stories that are there. So if you look at Task 37, IEABioenergy.com, lots and lots of data. When we look into the future and we look at future energy systems, we're looking at lots and lots and lots of wind, of solar. And if I take Ireland as an example, examples always help. So Ireland is an island and we have an island grid. In 2017, 25% of our electricity was renewable. And for 2030, we're hoping to have 70%. It's a government target. So on average, throughout the year, 70% electricity will be renewable and predominantly from wind. We have significant sea area in Ireland, and we have lots and lots of proposals for offshore wind, floating wind. Ireland as an electricity grid has achieved 70% system non-synchronous penetration. I do understand this is a world record. It means that at any one time on the electricity grid, 70% comes from variable renewable electricity. Now, if we look at having 70% on average throughout the year in 2030, and if we say the capacity factor is 35%, mathematically, we're then saying that peak production should be equal to 200% of average demand. And this is exacerbated by peak production at periods of low demand. So summer nights, when we're all in our bed, we don't have that cooling problem. We could have lots and lots of electricity. So power to X can be a biological battery. It can integrate electricity and gas. It's a means of changing the energy vector from electricity to gas or onto liquid for use in sectors that are hard to electrify. So we could look at electricity providing fuel for planes and ferries, but it would be a liquid fuel from power to X. What's very important in all this is that the electricity needs to be decarbonized to make decarbonized hydrogen. So if, for example, you make hydrogen from a coal power plant, you have a carbonized hydrogen. And if you look at our electrolyzer types, we have the AEC, the proton exchange membrane, solid oxidizing electrolysis cell. They're not, the efficiency is about 80%. So we actually exaggerate the carbon intensity of the electricity when we make hydrogen. So electrolysis is breaking water into hydrogen and oxygen. So work we've been doing with my good colleagues in MRI is we've been looking at, well, if there's a high wind forecast, it's a good time to pull down electricity because there'll be lots of wind and you'll probably capture that green electricity. Or when the price of electricity is very low, it typically means that wind is online, solar is online, and we have some of the power plants in the background. So what we have found in modeling this system in Plexus, that we can reduce the carbon intensity of the hydrogen as compared to the electricity that it's pulled down from. We can have a low cost electricity making a relatively low cost hydrogen. And the big thing is we can capture electricity that would have been curtailed. So if you look at the graph here on the right, we have options, so we can bid. So for example, if we bid at 4 cents a kilowatt hour, the red line, we're operating our electrolyzers at maybe 3,000 hours a year, and the cost of our energy is 200 euros a megawatt hour. So we're getting hydrogen that is quite expensive. If we bid at 6 cents a kilowatt hour, the green line, we're operating the electrolyzers for 6,000 hours a year. The cost of the energy drops to 100 euros a megawatt hour, which is about 4 euros a kilogram of hydrogen, which is a euro litre of diesel equivalent. So we need to have the electrolyzers operating for about 6,000 hours a year to have a cost sustainable source of hydrogen, and we can also get the curtailed electricity. And that hydrogen can be used in fuel cell vehicles, can go into a hydrogen grid, but at this moment in time, that market is not well developed. So we see great potential for hydrogen to be converted to methane. And we do that by upgrading biogas with hydrogen. And we have an option of in situ biological methanation. So we can put the hydrogen directly into the anaerobic digester. A problem with that is that the acetoclastic methanogens are going to produce carbon dioxide. So you'll always have carbon dioxide in the output, and you would probably need a gas upgrading system. So we can use an ex situ system. So here we have methanogenic RK, and what those guys do is they break down hydrogen and carbon dioxide to methane and water. You need 4 times as much carbon dioxide as hydrogen, and the carbon dioxide is converted then onto methane. So we have found that if you have an ex situ system, so the biogas from the reactor meets the hydrogen, and that's the only feedstock in here, and the hydrogenotrophic methanogens produce pure methane. So within our lab, we've looked at a number of these types of systems. So we've added hydrogen to the anaerobic reactor and found we still have CO2. The most efficient system was adding hydrogen and carbon dioxide in a batch ex situ system. So these guys here are only being fed hydrogen and carbon dioxide. And we have efficiencies over here of about 95%. So we know we can create a microbial fauna that eats hydrogen and carbon dioxide and produces methane. It becomes more problematic in a continuous process. And it also becomes problematic when you introduce methane into the system, because you change the hydrogen partial pressure, you increase the gas flow. So this would be, for example, if you upgraded biogas to biomethane and brought the CO2 to meet the hydrogen, you have quite a simple system. However, if you introduce biogas and hydrogen, it is a bit more complicated because methane is now in there as well. So what we have proposed is a number of strategies. For example, across Europe, there are around 17,000 anaerobic digesters. We could place electrolyzers at each of these digesters, and at periods of overdemand, or the farmer can enter into the market and buy electricity to make hydrogen, which can be injected into the existing digester, and you can improve the methane production, but you will still have carbon dioxide. But you can then have a second chamber, which would be ex situ, which will have the methane and the carbon dioxide from the digester and hydrogen from the electrolyzer, and we can get grid quality methane. We can also have a series of reactors where we're improving the ratio to get up to something which is grid quality. This is a plant that we talk about in our report. It's Electrolysis. They're in Denmark. So here we have an existing anaerobic reactor, which is producing 125 meters cubed of biogas, 75 meters cubed is methane, 50 is CO2. So again, with this Sabatier equation, we need 4 times the amount of CO2 as hydrogen. So we introduce 200 meters cubed of hydrogen that will react with the 50 meters cubed of CO2 to give us 50 meters cubed of biomethane, synthetic biomethane. We still have the 75 meters cubed of biomethane in the biogas. So we now have an output of 125 meters cubed of methane as opposed to biogas, which was methane and CO2. So we have a 67% increase in methane output. And we also have upgraded the biogas to methane, which could be put into the gas grid or could be used to run a truck. Again, in our laboratory, we have looked at how sustainable is this system. So we've looked at, for example, cattle slurry and some crops having an anaerobic digester. And we've looked at the idea of hydrogen from electrolyzers to upgrade the biogas to pure methane. So we are now replacing water scrubbers or membrane scrubbers in an upgrading process. And to cut a long story short, what we found, to meet the sustainability criteria in the Renewable Energy Directive, we need to have at least 85% decarbonisation of the electricity used to produce the methane. So we're really saying that it's all about electricity. If you have green electricity, you then have green hydrogen. If you have brown electricity, you have brown hydrogen. And we need those electrolyzers operating for at least 6,000 hours a year to be cost sustainable. We're then looking at, well, can we improve this process? Can we integrate this process? So this is a project led by David Wall in Marye and Cork, where we're looking at putting an electrolyzer in a wastewater treatment plant. So there is a wastewater treatment plant, there is a sludge digester, and in this project, we're in the Lower Harbour in Cork. There are 2 wind turbines, and the electricity is used by Depuy, but a lot of that electricity is not used on site. So we've looked at an electrolyzer that would take electricity that would be curtailed. It produces oxygen, which goes to the wastewater treatment plant. It produces hydrogen, which can meet the biogas from the sludge digester in an ex situ biomethanation system. So we're now producing biomethane that can be used as a transport fuel. And this is interesting because initially we have biogas, which was used to produce heat, which is maybe 2 cents a kilowatt hour of economic value. You're now increasing the methane by about 70%, and the sale value is probably 10 cents a kilowatt hour because you now are replacing transport fuel. So this can be quite economically advantageous. We are now getting a value for the oxygen, and we're involved in the circular economy system. We also have the potential to use the hydrogen in the fuel cell transport system when that comes online in a future situation. Now, we've done a lot of work with, led by Rich and Lynn, where we've looked at that system integrating into a bigger system. So for example, we again have the power to gas producing hydrogen and oxygen. The hydrogen can meet the biogas to produce biomethane, but we can also take the sludge and we can pyrolyze that sludge and make pyrochar, syngas, bio-oil, so we have more energy products. But the pyrochar can go back into the anaerobic digester and can go into the biomethanation and improve the process through what we call director-to-species electron transfer. So we can improve the anaerobic digestion process, we can improve the biomethanation process, and eventually the pyrochar goes back to land where it increases the soil organic content. Now it takes 100 years to make 5 millimeters of soil. So what we're saying here is the digestate can be pyrolyzed. It's almost 80% carbon. It goes back on the land. We're making soil, and then we can pull down more carbon dioxide from the atmosphere. For example, in Denmark at the moment, they are at 20% green gas in the gas grid from large centralized anaerobic digesters. And what they expect in Denmark is by 2035, they expect to match the demand for natural gas in Denmark. And they're not using energy crops. This is typically cheese facilities, distilleries, breweries, wastewater treatment, and slurry. But they're now looking at potentially introducing electrolyzers at these facilities, which will increase the yield of methane by up to 70%. So we have a country like Denmark that has significant targets for greening the gas grid in a circular economy system by treating waste, reducing eutrophication, improving air quality, and reducing pollution of wells. So it's very much a large integrated system. And they're also looking at digestate, because if you've large digestate, large biogas facilities, you've large quantities of digestate, which they can pyrolyze reducing the amount of digestate to go to land, and producing more products. A recent piece of work we've looked at is making methanol. So again, we're starting off with anaerobic digestion and manures and straws and biogas. But what we can do is we can have an electrically driven catalytic conversion of biogas to carbon monoxide and hydrogen, which can then be converted into methanol, which can be used in an internal combustion engine. So we now have electrolyzers producing hydrogen, biogas producing carbon monoxide and hydrogen, and together producing methanol. And I understand that Porsche are building a very large facility to produce methanol to be used in the very extensive fleet of old Porsche cars to keep them on the road and to keep them green. So it is an electrofuel in the form of a liquid. And when we take this further, this is a plant in Germany that is proposed, West Küste. So we're starting off here with offshore wind, producing hydrogen and oxygen. The oxygen can go to cement production to make it greener. Some of the off heat can go to district heating. The hydrogen from the electrolyzer can react with the carbon dioxide from the cement production to make methanol. The methanol can be used to make biokerosene. So we now have district heating, green cement, biokerosene from aviation from offshore wind. So we can see that not alone can we ramp up biogas for the day-ahead market electricity to match or to deal with the vagaries of temporal mismatch between energy demand and energy supply, but it can also be a sink for electricity that's produced at a time that it's not wanted. And we can make renewable methane, we can make methanol, and we can also go on to biokerosene. So we do see a significant role for biogas in treating waste at creameries, at food and beverage, at distilleries, at beer production, at municipal solid waste. We can react it with CO2 and we can make methane or methanol or other liquid fuels. So I want to thank you. I want to thank my colleagues in Marai who undertake this research with me. And thanks also from IEA Bioenergy Task 37. So we will take some questions, hopefully. I will stop sharing my screen and we can have any questions from the floor. Can you hear me, Jan?
Yes, I can hear you.
Have we any nice questions that we can deal with?
We take only the nice ones? Okay. There's, I don't know, I see here first question, Jerry, did you consider?
Direct hydrogen production from biogas via steam reforming. We have a report which has been led by Jan, and we're looking at all green gas vectors. So we are looking at hydrogen and we're looking at gray hydrogen, we're looking at green hydrogen, and we're looking at blue hydrogen. So typically we can convert natural gas to hydrogen and sequester the carbon dioxide. I think that's called blue hydrogen. Green hydrogen is from offshore, but we can also take biogas and steam reform it if we can sequester carbon dioxide. So I suppose one thing, our opinion in IEA Bioenergy is there's many, many ways of doing these things. And we are, I suppose the work we do in IEA Bioenergy is we look at all these different scenarios and we look at exemplars and we look at energy balance and we look at economics. So there are many, many ways of creating green gas.
I might add that the idea behind that might also be to create negative emissions, because you can separate the carbon dioxide then, and if you can either use it because it's neutral, greenhouse gas neutral, or you can actually store it somewhere underground, whatever, and then you could create with such a facility negative emissions. That's why, but we haven't looked into this into detail about costs or things like that. We have to see how the hydrogen market is developing and then what the price is. And I think, in my opinion, that biomethane based on waste material, for instance, might be cheaper than electrolyzes for such purposes. I would go to the next question then. Is it easily recover biogas from other sources? Various inhibition is involved. This is process dependent. There are options to deal with inhibition. If you have a high nitrogen content or salt content or things, there are various applications worldwide where they can deal with it. AD plants' income is mainly on government subsidies. Zero emission law is enforced. How can AD be sustained? That's a very good question. I don't know where the price for CO2 will end up if zero emission law is enforced. This is the question there. CO2 abatement costs of biogas are quite high, agreed. There are other benefits coming with biogas, which might be worth looking into in order to get also other sources for revenues. But really the question is where the price for CO2 will end up. And then if we know this, and if you can tell me that, then I can tell you if biogas is viable or not.
I think as well as we progress to 2030 and 2035, the low-hanging fruit of decarbonization will happen first. So we will have our electric cars, we will have our deep retrofit, but then we're going to be faced with agriculture, we're going to be faced with enteric fermentation, we're going to be faced with large industries such as cement production, steel production. And I think at that stage, when we're looking at the very hard to decarbonize sectors, including for ferries and aviation, I think at that stage, the solutions will include power to X, will include anaerobic digestion. And I do believe that anaerobic digestion can be quite expensive, but it has to be understood that it is a waste treatment system. It also cleans water, it reduces pollution in wells. And it will be very interesting to see what happens in 2030, 2035, when we've done the easy stuff. How do we do the hard stuff?
There's now a question. How about using H2 directly as energy source? H2 is costly to get, but CH4 is very low priced. How do we get extra methanogen? Think about sustainability. Jerry?
I suppose the concept here is that, like from my perspective, there's lots of areas that are very, very hard to decarbonize. I mean, if you're looking at cement production, you're going to have CO2 coming out the stack. We're going to build things in cement. We might build renewable energy systems with cement. You have the big slab for your wind turbine. Like when you're getting to that idea of decarbonizing cement, decarbonizing alcohol production, I think at that stage, biomethane will become quite a competitive system. We have a paper coming out at the moment where we're looking at aviation, we're looking at ferries, we're looking at haulage, going over long distance. Electricity will not take a plane to Australia. We're not going to have a hydrogen fuel cell taking a plane to Australia. I think there are so many questions in the whole realm of decarbonization that you come up with a matrix of this is a viable solution. It is more expensive than electricity, but electricity is not going to power that plane. And I think when you look at the whole integrated system and you look at all sources of carbon and energy, you will find that biogas does offer solutions in places. And I think as well in that people do talk about batteries. If we look at, if we're going to have 90% green electricity from wind turbines, there are going to be periods of time where there is too much electricity and we can spill it from the system. But it does give us opportunities to take that electricity as hydrogen and react with CO2, be it in the 15,000 digesters in Germany, or be it from cement manufacturer, or be it from alcohol industry. But I do think that we need as many options on our menu as possible to deal with the outputs in our energy system and in our food system and in our agricultural system.
Okay, then
I suppose the question here on corn and maize, I know that's quite dominant in in Germany, and then in Denmark it's not. They don't have energy crops in Germany. Do you see maize continuing in Germany for long periods of time, Jan?
No, they reduced the allowed amount in the subsidy schemes, in the future subsidy schemes. I don't know what the actual, right now we are in the process of negotiating a new subsidy scheme. I think it's 50%, something like that. It's going down. Energy crops is a question. They bring a lot of energy into the production, other than manure. But of course, energy crops are, the sustainability of those are questioned, and then on the other side, the land use is also discussed. But I think sometimes you need energy crops in order to increase the capacity of the site. If you have a waste material or residue, which is only available in a low amount and not enough to have a production large enough, then energy crops might help. And also, of course, marginal lands or even polluted areas, then energy crops, I think, have their justification.
John O'Shea is asking about 6,000 hours per year of utilization required for electrolyzers to be cost effective. What we have found is that we don't see cheap hydrogen. Even if electricity is cheap, you still have the electrolyzers, you still have transport of hydrogen. I don't see hydrogen being cheaper than €4 a kilogram, which is about 10 cents a kilowatt hour. And from my perspective, I don't see hydrogen used as a source of heat, because you can have a wood chip at 3 cents a kilowatt hour. From my perspective, if you take hydrogen from offshore wind and you have a system of producing hydrogen, you will be looking at the e-refinery. You will be looking at hydrogen in refineries. You will be looking at hydrogen for transport fuel, such as aviation. But I don't see hydrogen from offshore wind being as cheap as natural gas. I really don't. And Angie is asking then about eye-watering, expensive hydrogen from electrolyzers. Yeah, I think if we get to €4 a kilogram, we'll be doing really well. I mean, electrolyzers may become cheaper, but there is, you have all this cabling, you have the offshore wind. It's never going to be natural gas level of price. It's going to be expensive. And I do believe that when we get to the top of the tree and we're after aviation fuel and ferries, it's going to be expensive to do that. Have we factored in the increase in use of electric cars, heating and demand side management? One of the things electric cars do is they reduce the energy to run a car. So you have a huge reduction in energy spent because the electric car is so effective. And there was a paper published that if you had 100 kilowatt hours of electricity, you would have propulsion of about 65 kilowatt hours in an electric car and only 20 kilowatt hours of propulsion in a hydrogen car. So the cheapest system is the simplest system. When you start having a cascading going from electricity to hydrogen and hydrogen onto methane and methane onto methanol, you are getting more expensive. So the cheapest energy will be green electricity. And as we go along the X, it's going to get more expensive.
There's a question from Franz Kirschmeier. At which methane content do you see biomethane being upgraded to natural gas equivalent so it can be directly injected into the gas grid? Yeah, this depends on the gas grid, I think. That's the point. I mean, we have a lot of discussion about these standards, and I think you know this very well, Franz. So this is the question here, how this will develop. I mean, at the moment, natural gas is the standard, but in the future, we might see other standards also with the hydrogen content in the grid, because they have also to adapt to the new situation. And therefore, I think this is in the future, in the long-term future, this is under negotiation, of course. Which share of hydrogen will not be converted to biomethane? I don't really get this question. Because
there is a perspective that we can, in the future, put hydrogen into the gas grid. and we can take hydrogen to combined cycle gas turbine plants. I know, for example, in Ireland, they have this concept of 37% biomethane in the gas grid and 13% hydrogen in the gas grid. So they do see the gas grid as a vector or as a way of carrying hydrogen, and then it could go to a combined cycle gas turbine. So you could have biomethane and hydrogen going into a CCGT plant at 65% electrical efficiency. When we start building new gas grids for hydrogen, it will be expensive. Like, my understanding is we probably spent 4 billion in Ireland on a gas grid. If that is redundant and you start putting new pipes in the ground for hydrogen, that becomes a very expensive system. So the more we can use existing piping, the better off we are. And that may be a combination of hydrogen and biomethane. Mohammed Tabassium is asking about integrated solar biogas systems. There is an area, microbial electrolysis cells, where you can actually have an anode and a cathode inside in the anaerobic reactor. And you can almost have a power to gas system without an external electrolyzer. So you can have an anode and a cathode, and you can react the CO2 and get more methane out. And that seems to be a more efficient system. There's also potential to use sun within an anaerobic reactor type system with the anode and the cathode. Those technologies are probably, I would think, 10 to 15 years away.
There's a question here if biomethane can replace natural gas in large gas turbines. I would simply say yes, because biomethane has to meet standards of the natural gas grid. And so you actually can make, with, of course, with quite an effort, 100% methane out of biomethane. And then this is possible to run any natural gas application with biomethane.
There's a conversation here from Rohit Bedhara about flexibility will not be cost effective at the farm level. So are we pointing towards larger 5 megawatt projects in Europe that are more integrated? I'm relatively familiar with the Danish model, where they have large anaerobic digesters up to 15 megawatts. And I believe in a future scenario that there will be a cost for facilitation. And I do think in the presentation of Jan, like the ability to ramp up and ramp down and to fill in when PV isn't working. So if it's nighttime and PV isn't giving you electricity, I do see potentially, as we get to the top of the tree, that if a biogas system can operate at nighttime when the PV isn't there, or if it can operate when the wind isn't blowing, I would imagine that the expense of the biogas can be recompensated when you look at the entire system.
There's a discussion about how this is economically viable, beneficially. Is there a few possibilities to run a flexible plant beneficially? I mean, the idea of the report was to show actually the technical capabilities. So we wanted to show technical conditions, and we included the economic aspect to give an idea. We haven't looked into that quite deeply. But when you really look into that, then of course, first question is biogas electricity actually possible to sell at the price you produce it? And then, of course, the flexibility comes as a next point here. And as answered before, I think the big question is how the energy system of the future, how the prices will look like. In Germany, we have the situation that tariffs now go down because electricity is considered to be most expensive. And now some farmers think about to actually replace their own or their electricity supply from external sources by the biogas plant they have, because they pay much more for the electricity coming from outside than they need to produce the electricity. So there are, I think there are applications where this is possible to make biogas beneficially. But the big question, in my opinion, is how the future will look like, how these prices will actually develop once we really go into a CO2 neutral world, and all sectors need to be CO2 neutral, I think. And then the story will be completely different.
There's a question here from Nesreen Ben Yahmed about the utility of green methanol. Again, it's probably a solution to a particular problem. I know in Denmark, they're saying, look, there will probably be, 1 million internal combustion engines on the road. Like Land Rover always talk about their Defenders have been driven for the last 50 years. You have these old classic cars. So methanol is a way of allowing you to have an old classic and you're running it on a relatively green fuel, which has come from electricity or which has come from biogas. An area that I'm quite interested in is, again, it's our latest paper. We're looking at aviation. We're looking at ships. We're looking at heavy trucks that transport long distance. They're not really going to be electrified. I think it's highly unlikely I'm going to get on a plane to Australia. We do need liquid fuels. And when you look at the biomass resource, it can be relatively limited. But when you look at electricity, there should be large quantities of electricity that offshore wind and onshore wind and PV is coming down to 3 to 4 cents a kilowatt hour. To me, the hydrogen will be about 10 cents a kilowatt hour, but that will get you on the road to methanol, to ammonia. You can be powering ships, you can be powering planes, you can be powering heavy haulage. And to me, they will be more expensive, but that is the role of methanol and synthetic compressed methane, for example. It's those areas that aren't easy. And the follow-on question from Kataswara Rao Puta is, what should be the cost of renewable power and electrolysis units to make these processes economical? Again, I believe that hydrogen at best will be about €4 a kilogram, which is about 10 cents per kilowatt hour. And it's when you can't power a truck on electricity, that's when it becomes economic in the sector that can't be decarbonized.
There was one question regarding the size of the plant, or several questions here about this. This example which I had from Switzerland, this is just a bundle of several small-scale plants, and then the virtual power plant means that the production of these plants are bundled together, and the virtual power plant operator sells the sum of the electricity from all these small-scale plants. I think this is the future of the marketing of these small-scale decentral plants. There's also a question of economy of scale here. The problem with bioenergy is you need the supply of the material, of the substrate. And you can't build huge biogas plants, or you don't want to, because then you have to supply them with the substrate. And this might be an option at some places of the world where feedlots or animal husbandry is concentrated a lot. But as soon as you have slurry, transportation means you carry around water, and this is expensive. So I think biogas will stay in an order of magnitude where you have a decentral solution, and you need to think of how to combine all those decentral solution by virtual power plants rather than increasing the size of the plant. And there's also a question here, the proper management of the leachate. We call it digestate after anaerobic digestion. This is also coupled with this point of order of magnitude of the plant. If you have large plants, you have huge amounts of digestate, and the proper management is direct application on agricultural land as a fertilizer. And if you have a huge plant, you simply do not have enough land around to get this properly applicated. You will put your groundwater into danger. That's why decentral small-scale plants are rather a solution than large-scale plants.
Another area in digestate is that it can go to pyrolysis. And in pyrolysis, what you would typically do is you would segregate the liquid and the solid. And the solid could go to pyrolysis, where you can produce pyro oil, syngas, and pyrochar. And pyrochar is seen as a negative emission technology because when you add pyrochar to land, it increases the soil organic carbon. And I read recently it takes 100 years to make 4 millimeters of soil. But if we put pyrochar on land, we can increase the carbon content. We can pull down more CO2 in photosynthesis. We can increase crop yield. But there are solutions. We can manage digestate. We can have ammonia stripping. We can pyrolyze. So one of the things we do is we are trying to raise that there are lots of options. There are things you can do. And IEA believe that we can ramp up biogas production almost by a factor of 3. And when I look at that, I start looking in my home country of Ireland. I'm looking at cheese manufacture, and Ireland is responsible for 15% of infant formula. But all of these food and beverage industries have large quantities of wet organic waste. And therefore, you're looking at digesting wet organic waste from food and beverage, and you've large quantities of digestate. And then they don't want to be managing a nutrient management program for farmers. So you do have options to pyrolyze or to condense carbon in digestate. So there are solutions for lots of different problems.
Franz has updated his questions on the biological methanization. So which share of hydrogen will not be able to convert in those methanation process? That's a standard process engineering question, because usually these systems have a certain throughput of the gas. And if you look at what companies who offer these technology give you on the numbers, they usually give you a very high methane concentration in the product gas and a very high production rate. But you should ask, if you see these numbers, if they are measured at the same process conditions, at the same throughput. Because if you reduce the throughput, then the H2 has, of course, a longer retention time in the system, and it is more easily eaten up, and your remaining gas concentration in the off gas is very low. But if you increase the throughput, your methane production rate will increase, but then, of course, you also will have a lot of hydrogen in the off gas. So I think it depends a little bit on which technology you have. They also, some work with pressure, some work with mixing. And the question is always, how do you get the hydrogen into the liquid phase? Because it's not very easily soluble. And depending on all those factors, it depends how much hydrogen you have in the off gas. I mean, if you really opt, or if you really aim for direct grid injection, then this is a question. But if you have an upgrading step after the methanization, I think hydrogen is easily to separate from methane, because it is much smaller than methane.
There's a question here from Thomas Muraja on algae. How you see concept of algae instead of electrolyzing, and use algae as additional source of biomass for digester. We've been doing some work in microalgae, and we see great potential for a photosynthetic microalgae upgrading system. So we do see taking biogas into a carbonate bicarbonate cycle and having the microalgae integrated into that cycle. The microalgae, in effect, can take the CO2 that was in the biogas to grow, so you can produce microalgae. Now, our perspective is microalgae has a very high value in the biorefinery world, whether as a feed or being used to make products. So we do see microalgae used in a biogas system, but used to upgrade biogas to biomethane while having a product that can have a higher value. So we see potential for anaerobic digestion to be integrated in a biorefinery world and having products beyond biogas or biomethane, but having other products. We have digested microalgae, and it does digest. We've also looked at macroalgae, which is seaweed. We've done some lovely work on digesting seaweed. It is very, very digestible. But again, I can go to my local delicatessen and pay €4 for 40 grams of seaweed. That works out at €10,000 a ton. You're not going to digest something that costs €10,000 a ton. When I go to China, I'm always fed Saccharina latissima. So I think there are feedstocks that can be used for anaerobic digestion, but it may be economically better to use them in a biorefinery or as a food.
There is one more question. Can electrolyzer as part of demand-side electricity grid balancing be effective at a negative electrical price? Of course, it can be. I think that was a major idea of the whole surplus energy demand. Everybody thought electricity will be for free in the future. I think, at least in Germany, this discussion has been changed a little bit. So now we are opting for electricity at low prices. Discussion in Germany, hydrogen shall be produced in Northern Africa and then transported to Europe. Because it doesn't make sense to have electrolyzers sitting for 3,000, 4,000, 5,000 hours a year and then not operating them. That's why this grid balancing effect of electricity of electrolyzers is kind of out of date, at least in Germany. However, the combination of a biogas plant and electrolyzer is, of course, an interesting question. But then the question is what to do with the hydrogen. So CHP off in times of negative electricity price, electrolyzer on, then you would feed the hydrogen into the process, produce methane, then use it in the CHP again once the electricity is needed in the grid. I see that as a very expensive solution, and I don't think that this is in the actually near future technology which we will see, because it's simply too expensive.
There's a question here from Franz Kischmeyer talking about the methane content after methanation. Can it be 85%, 95%? Jan mentioned this earlier. We talk about the methane evolution rate. It's how much methane you get per unit reactor. We have got over 95% in a batch system, batch ex situ. It's very easy to get over 95% methane content. When you add in carbon dioxide and methane and hydrogen, you need a bigger reactor because the methane is now part of the gas, reducing the retention time. When you have a continuous process, it's harder to get those numbers. So the answer depends on what you want. You know, you can get very high levels of methane in a batch system, but a batch system is expensive. It's easier to biomethanate carbon dioxide and hydrogen than carbon dioxide, methane and hydrogen. So again, there are a range of answers and a range of solutions depending on what the outcome is desired.
Sorry for interrupting you. We're running out of time, so if you want to select one last question.
The future of dry anaerobic digestion as compared to wet anaerobic digestion. I've seen these systems in Munich. The waste management in Munich is the KEDCO process. So you just put waste into it's like a ro-ro tank, and you add water and you add heat. It's very simple, no moving parts. It's a simple technology. However, it probably doesn't get you the same efficiency as a continuous process. I suppose one thing I would say, there are many, many, many applications of anaerobic digestion. There are many feedstocks, there are many solutions, and I would encourage people to be open and to accept the role of different technologies for different inputs. Jan, any final words?
I think it depends on the substrate, and then you have a substrate with a high solid content, then you would opt rather for a dry digestion system. A lot of disturbing material, solid waste, things like that, you would go for a dry fermentation system. Manure, lots of water in it, liquid, easy to pump, industrial liquid waste, easy to pump, then you go for a wet system, and everything in between you choose. So I think they both have a future. So they will work depending on the substrate.
Thank you all for the time taken to listen to us. Thank you very much to Chiara and Ernesto and IEA Bioenergy for hosting us. So I've thoroughly enjoyed the presentation. Thank you, Jan. I enjoyed your presentation very much.
Same to your presentation, Jerry.
So we'll see you all. Thank you very much, guys. Thank you.
Thank you. Bye-bye. Thank you.
Bye.